Hello there. This week we'll be talking about transformations, and let's just start with a relatively simple one: translations. So let's use the Cartesian plane. It's usually the easiest for this. And let's say you have a shape, a circle, and if you're translating it, you're basically moving it around. Like imagine you have a hockey puck and you're just tossing it around the arena. The hockey puck won't change its shape, and also you're not really supposed to rotate it either. This doesn't really matter with a circle, but if you have something like um, a square, you can't rotate that. Anyways, that means to translate it, like say you're translating it right, then you just get a circle here. You can also translate it up. Actually, that's down. I mean, down, or you can also translate it up. You can also translate diagonally, but in that case, you usually think of it um, break into components first, move it right, then move it down, instead of just thinking of it moving directly diagonally. And a translated figure, or really just any sort of transformation, if we say this original circle is A, we say this new circle is A prime. That's usually how it's denoted. And if we have a triangle, um, triangle A, B, C, and we translate it here, we usually denote it as A prime, B prime, C prime. Or we can just write it like this. Um, a translated figure, since you're not doing anything to it other than moving it, it's congruent to the original figure. And if we're using something called mapping notation, it would be written like this: x, y, where x and y is like the original point, and then it turns into x plus a, x, sorry, not x, y plus b. And this is assuming that you're taking a point and moving it a units right and b units up. And just as a note, like in this case, it goes by Cartesian. Positive is right, and positive, like vertically, is up. And like I said, this is in the Cartesian coordinate plane. If you're doing polar coordinates, then the notation's a bit different. And just as kind of a general rule, translation of a function f of x, let's just say it's a simple one, y equals x squared. Now, if you think about it, if you want to move it down, then you would do something like f of x minus 2. And then in that case, you shift everything down and you get a function like this. And if you want to shift it like left and right, then it's a bit more complicated. But if you think about it, the origin here is when uh, x squared is equal to 0, but if it was here instead, like say this is at 1, then that means for y to be 0, then this has to be x minus 1 squared or something. So, as a general rule, when you're translating something and only translating, um, it would be in the form of x minus a plus b, and a is how many units it has been moved horizontally, and b is how many units has been moved vertically. And also, when you're moving it horizontally, like the f of x minus a, the reason I'm using the minus is because it kind of goes opposite of like what's intuitive, sort of. Because if you're moving it right, you have to do minus, and if you're moving it left, you have to do plus, which makes sense if you think about it, but it's also something weird to consider since it seems backwards. Anyways, next is rotation. And usually you rotate it around the origin, but you can really rotate it around any point. Just as an example, say you have a triangle like this. If you want to rotate it, we'll rotate it counterclockwise in this case. You just get a new shape like this. And I drew that wrong, sorry. and that is not to scale. Close enough, I suppose. Rotation's usually a bit annoying to work with in Cartesian form. That's why a lot of times when you do rotations, you use polar coordinates. And in case you don't remember, for polar coordinates, the equation is r theta, where r is the distance from origin and theta is the angle there. It's easy to do rotations like that. So I guess we'll use it that way. So also you have to note which direction is rotating. Usually we say that counterclockwise is positive because the angle is getting bigger. So then using mapping notation, it would be something like r theta turns into r theta plus a, where a is like the rotation angle. And also the rotated figure is congruent to the original figure. It's still the exact same shape. You're not twisting it in, well, you're not warping it in any way. It's still the same shape. It just rotated. And in a rotation, all points in the rotated figure are the same distance from the center as the original figure. In this case, we're rotating around the origin, but honestly, you can rotate it around any point. You can rotate it around this point. You can rotate it around this point, and basically what you're trying to do is just the distance between the points has to be the same, like between the point of rotation and the original point. And if you're rotating like that, it would, I suppose it would look something like this. Though overall at the end you're usually rotating around the origin, so you don't have to worry too much about that. And I guess a way to think about it is whatever the point of rotation is, it's the center of the universe, so to speak, and you're kind of just turning around there. Next we have reflection, and just think of it as mirror image. So let's say you have a square here. Actually, not a square. How about a triangle again? And if you're reflecting it, just imagine it's a mirror. You can either reflect it across the y-axis, x-axis, or just any line. If you're using the y-axis, then it would look something like this. If you're using the x-axis, it would look something like this. Also, it's possible for you to do the line like this is the y equals x line, then a reflection will look something like this. Usually, the only lines you would reflect it across are y equals 0, also known as the x-axis, x equals 0, also known as the y-axis, or y equals x, which is like this line here. Usually those are the only lines you'd reflect it across. And in reflection, all points in the reflected figure are the same distance from the center as the original figure. And the reflected figure is congruent because, once again, you're not warping the shape, all you're doing is reflecting it. And I guess one way to do a reflection is to draw a straight line from each point to the center point and continue each line for the same distance to create the new points. So like here, draw a line here, continue this line, same distance away, draw a line here to center, continue drawing the same way here, and eventually you get the reflected figure. And, well, I mean, you usually wouldn't do that for reflecting across the x-axis or y-axis, but if you have a strange line, like if it wants to reflect it across something like this line, then you might want to do that. Also keep in mind you usually only reflect across straight lines, so if it's telling you to reflect across something like reflected in terms of this equation y equals x squared, I'm really not sure what that means, and that's probably never going to happen. Next we have distortion. Now distortions are also known as stretches, and they are vertical stretches or horizontal stretches. So I guess you can think of it. I'll use a simple example. The generic equation y equals x squared. If you're compressing it, then compressing it horizontally, it turns into this, or you can widen it like this. And you can also make it, you can also squish it or stretch it vertically too. So it looks a bit similar, but it's really different. And then usually it would be notated as x, y turns into ax, by, where a is how much it's stretched horizontally and b is how much it's stretched vertically. Now going back into function notation, if we have function f of x, then this would turn into bf of x over a, and this is corresponding to this mapping notation here. Why it's the reciprocal? Well, if you think about it, it makes sense, because then that way you need like a bigger value for x for it to be the same as before. Now, the thing about distortions, which kind of differs from everything before, is that they do not maintain the shape, because you're actually changing the shape, and it's also not guaranteed that you'll maintain the position either. Like, just as an example, if you have something like this, and you're, let's say you're compressing it vertically, the thing is, you wouldn't just compress it vertically like this. Instead, you'd compress it vertically like this, because when you're compressing it, like when you're doing distortions, you're doing it really in terms of origin. So then if this has to get squished down, you're also really squishing down the location of the vertex as well. But if there are points that are the same, like for example, this point is the same even if it's stretched, if it's distorted, those are known as invariant points, basically points that don't change. And this really applies for any translation, except it usually is only used for rotations, reflections, distortions, and I suppose dilations. And I guess since I already said that, the last type of translation, last form of transformation is the dilation, where a figure is magnified about a certain point. So let's say you have a shape here, and if you're dilating it, you can imagine drawing a line through all the points here. And really what you're doing is magnifying it. And as you can see, when you're doing a dilation, well, these are supposed to be similar triangles, I just drew it badly, but otherwise what you're changing is, first of all, the position, and you're also changing the size. But the angles are remaining constant. You're really just making it bigger. And these problems can be solved using the principles of similarity, and basically you can do the things I drew here, the way I did it here, just by drawing lines through it. And they're magnified around a certain point. This point could be the center, and in that case the position wouldn't move, it would just get bigger like this. Or it can be a point outside of the triangle, in that case it would shift a bit. And I guess that's really everything to do with transformations. I missed a bit of stuff about function notation, but to be honest, you usually won't really need that. And I guess just as first to recap, translations, rotations, and reflections preserve collinearity, area, shape, and angles. Basically, they don't change the shape at all. And translations also preserve orientation, so you're not going to twist it around. And dilation and distortions do not preserve area. They also, distortions also don't preserve position sometimes, or really a lot of times, except for a few specific points. And dilations, they still preserve angles. And I guess as a recap, Translation is when you're moving a shape, actually just draw a smiley face. When you're moving it somewhere, this is a translation. A rotation is where you're taking the smiley face and rotating it around. A reflection is when you're taking the smiley face and reflecting it across some line. Then a distortion is where you're taking a smiley face and you're stretching it out. And then the final one, try and squeeze it in here, I guess. The dilation is where you're taking a smiley face. Let's just do it about the origin, and you're making it bigger. Yeah, finally, I'll just leave out with the question. Find the reflection of the points. Okay, so you have a point 2, 2, and you're reflecting this point across the line x plus 2y equals 4. Now this is a line, and you're reflecting it across that. And just to reiterate, you have this point 2, 2. You're not reflecting across the x-axis. I mean, the y-axis or the x-axis. Instead, you have a line, x plus 2y equals 4, and you're reflecting across that. That's your first question. And the second question, okay, so you have point Q, which, so you have point Q, which is 9, 14, and you have point R, A, B, and say they are symmetric with respect to the points. So symmetric to respect to points 5, 3, and the question is, what is A and B? Anyways, that's this week's lesson. Sorry for being a day late, and anyways, see you next week.